Afternoon. Go.
Can you hear me?
Yes, I can hear you.
Okay, thank you.
And you can hear me? Yeah, I hope so.
Yes, well, very well.
Okay. So the problem with the Zoom is fixed that there was the other time. Well, whatever. Well, okay. Hope that more people will still show up, but maybe I can. I think I will start now. Okay. So we were talking about tangent spaces and non-singularity. So now I first dealt with the case of hypersurfaces in a fine space. Now I want to deal with general affine algebraic sets first. So let's look at the tangent space of an affine algebraic set. So first introduce the differential of a polynomial. So definition. So let f be a polynomial in n variables and p a point in an. So then the differential of f at p is defined in the usual way of whatever differentiality. So dpf is equal to the sum of the partial derivatives f by dxi at p times xi. So as you see, this is a linear function, a polynomial of degree 1. If you put this into this is just a number. So as a linear function, I can also write this just as df by dx1 until df by dxn, so at p. So just as this 1 by n matrix of derivatives. So this gives me a map, a linear map from Kn to K. So linear map. Okay. And as you know from analysis or differential geometry, the differential, like the derivative, satisfies some kind of Leibniz rule. Namely, that if I take the differential at p of a product of two polynomials, this is equal to the differential at p of f times the value of g at p plus the value of f at p times the differential of p of g. This is all can be checked by straightforward calculation, and it's also standard. So now the tangent space So now let X in AN be an affine algebraic set. Don't in the moment need its variety. Then the tangent space, a point in X, and the tangent space of X at P is TAX, which is just the zero sets of all the differentials. So maybe I should have called, so this is called differential of F at P. So the zero set, the tangent space is just, I could either say it's the intersection, is the zero set of all the differentials of F at P, where F is an element in the ideal of X. Or if you wish, you can also to see that it's actually, so a vector space, you could also say it's the intersection over all F in the ideal of X of the kernel of the linear map that I just wrote down, the F by D1 at P, F by Dxn. This is, so by definition, therefore, TPX is a subvector space of k to the n, if we are, if X is in AN. Okay, so this is the tangent space. One should maybe mention, so just as a remark, if, say, assume for simplicity that our point is the origin, so at the origin in AN, the differential at the origin, so this is the point 0, 0, 0 of F, is the same as the part of degree 1 of F. So therefore, in this case, TP T0 of X would, if 0 is a point in X, is just the zero set of the homogeneous part of degree 1 of F for all intersection of the zero sets for all generators. So you can, in this sense, see that it's in some sense a linear approximation of X, because it's the zero set of the linear parts of the polynomials. If the point is different, you kind of just take the differential of F minus F of P. So I mean, it's you can easily reduce to the case that the point is the origin. Okay, so this is very simple. So, as usual, P in X is called non-singular point. If the dimension of the tangent space as a vector space is equal to the dimension of X, well, I could say the dimension of X at P, by which I mean the maximum over the dimension of Y, where Y is an irreducible component of y passing through P. I mean, soon we will anyway restrict to the case that X is irreducible, so then it's just then it would just be the dimension of X. And in fact, one can prove, but we haven't quite developed the method, that if a point is a non-singular point of a variety, there cannot be more than one irreducible component passing through P, but that requires that requires a non-trivial proof, and we don't have it. Okay, so if two components intersect at a point, then it will always be a singular point. But that's in the moment we can't prove that. But it's an easy exercise to prove it for hypersurfaces. Maybe you can try. Okay. So, and otherwise, X is called a singular point. And as before, we have X reg, the set of all non-singular points, and X sing, the set of all singular points. So just one stupid remark. Obviously, it doesn't make much sense practically to compute the tangent space in this way. In theory, you have to take the intersection of infinitely many such things, but finitely many are enough. We can also just take the generators of the idea. So let Ix to be generated by some polynomials f1 to fr, then X lies in AN, then tangent space X at P is just the zero set of the differentials of these polynomials. For P and X. That's actually basically trivial. Still, I can prove it. So TPX certainly is contained in this zero set. Because these, or the Fi, all lie in the ideal of X. So it's the intersection of all of them, and so one has to show the other inclusion. So this is clear. So now let H be an element in Ix. Then we can write H equal to sum I equals 1 to R, HI times Fi, no, because it's in the ideal, because the ideal is generated by those. So where the HI are some polynomials. And thus, if we take the differential, this is equal to the sum I equals 1 to R, and we apply the Leibniz rule. So we have HI of P Fi plus HI times Fi of P. But the Fi lie in the ideal of X, and P is an X, no, P is a point in X, so this is equal to 0. And so we see that this is in the subspace generated by the. So every element, for every element H in the ideal, I can express the differential as a linear combination of the differentials of the generators, and so the zero set is the same. Okay. So, what? Oh yeah, equal to 0. That's what I hopefully said, but I didn't write. Yeah, thanks. So we can also, if we have, like in differential geometry, if you have a morphism or polynomial map of affine algebraic sets, you can get the differential of the map, which is, just in some sense derivative of this morphism. So definition. So let X in AN, Y in M affine algebraic sets. Let phi be a polynomial map, so which is the same as all the morphisms, F1 to Fm, from X to Y, be a polynomial map. So the Fi are some polynomials in the first set of variables. So then the differential of P at the point P in X is dP phi, which is just the map whose components are the differentials of the Fi. So, okay, and I claim this goes from dpx to t y. So a priori, you can see this is, so a priori, this is a map from A to the N, or from, I could say from K to the N, because I take these differentials as input, take an element in K to the N to K to the M. But the claim is, you can check as an exercise, if I restrict it to this tangent space, which is a subspace of this K to the N, then it maps into the tangent space at phi of pi. We'll check that dp phi maps tpx into phi of p. Y. Okay, and that's again, you have to just use the definitions so that if you know that here the tangent space is the zero sets of the differentials of an ideal of this, and here is of an ideal of this, and the fact that this maps x into y will imply that this is true. It's an easy exercise which you can try to do. Okay. Okay, and so if one has this, that one, obviously it's clear that you take the differential of the identity on x, this is at the point P in x, this is equal to the identity of the tangent space of x at P. And if I take the differential at the point P of a composition of two such maps, two polynomial maps, this will be first you apply dp phi and then d phi of p psi. Now this is like the usual thing how you take derivatives. Maybe I should also say here to make it easier or to make it more concrete, note this differential, if I view it as a map from Kn to Km, is just given by the Jacobian of this map at P. So note that phi is equal to the Jacobian of F1 to Fr at P, namely to the matrix which is given by this derivative dF1 by dx1 until dF1 by dxn and so on dFr by dx1 dFr by dxn. So by which I mean as a map from Kn to Km, we just take so all of this at P, obviously. So we just do the map by applying this to a vector A1 to An, and we get an element there. So this is, as usual in differential geometry and analysis for maps from, it's just the usual differential of a map for that you have learned of in second year or whatever, third year analysis in Rn. Okay. And so we have this. So in particular, if phi from x to y is an isomorphism, so of a fine algebraic sets in this case, so it means it's a polynomial map which has a polynomial map which has an inverse, then the dp p from tpx to t phi of p y is an isomorphism of vector spaces for all p in X. So in particular, we see that isomorphisms send singular points to singular points, non-singular points to non-singular points, and so on. Maybe I don't. Let's look at some. So that's the wrong page. Yeah, so just an example. So let's say, and now this is not an absolute state, but often if a morphism, say phi from x to y is not an isomorphism onto its image, so say a surjective morphism is not an isomorphism, then either phi is not injective, or the differential P of phi is not injective. So I'm not claiming this as an absolute thing, but it's just something, most of the time that's the way how it happens. In fact, so if one wants to show that something is not an isomorphism, maybe the first thing that one checks is this. So either it's not surjective, or it's not injective, or the differential is not injective. And if that fails, then one has to start thinking. Not that then it's so. In particular, for instance, if we look again at our Caspel cubic, and we had this map t squared. So if t is the coordinate on A1, t to the third from A1 to C, which is a bijective morphism, as we had seen, but not an isomorphism. Now the inverse was a rational map which was not defined in the point 0, 0 on C. And we can also see in this case the differential is not injective, because if I take differential at the point 0 of this map, t squared t to the third, that means we just take these derivatives, 2t, 3t squared, but we apply it at t equal to 0. This is just 0. So it's the 0 map. In particular, it's certainly not injective. So also say if X in AR is a subvariety, then obviously just by definition, the tangent space at the point P, where P is a point in X, is a subvector space of K to the R. So in particular, we see that thus the dimension of TPX is smaller or equal to R. So therefore, if you have a variety which has which at some point has the dimension of the tangent space bigger than R, no neighborhood of this point can be embedded into AR. Or at least X cannot be, let's say just for now that X cannot be embedded in PR. Thus, if TP, dimension of TPX is bigger than R, X cannot be isomorphic to a subvariety of AR. Sometimes because, and I mean more generally, if X is a subvariety of a non-singular variety of dimension R, then basically by the same argument, the tangent space of X at the point P will be a subvector space of the tangent space of this ambient variety. So it means also if the dimension of the tangent space of P of X at P is bigger than R, it cannot be a subvariety of a non-singular variety of dimension R or smaller. Because of this, this tangent space is also called the embedding dimension of X at P. So if a variety has a very bad singular point, it means it cannot be embedded in a small affine space. Okay, so now I've done things in the case of affine varieties, but obviously we want to make it work in general, and we also want, maybe it's very useful to have this very elementary concrete description in terms of just the elements of the ideal if one wants to do computations with concrete examples, but one wants also a somewhat more intrinsic and abstract notion which one can use to prove theorems or to work with in a more general context. And so I want to give an intrinsic definition of the tangent space which works then for any variety. This is a bit more abstract and not so maybe quite obvious. I can't even write it, but anyway, the tangent space. So we take, let X be a variety, and P a point in X. So I want to give an intrinsic definition instead in terms of the local ring of X at P. Give intrinsic definition of TPX in terms of the local ring of X at P. Okay, and how does it go? It's the following definition. So we have, under this assumption, TPX. So let's say let MP be the maximal ideal in OXP. So then tangent space X at P, yeah, it's so you take the maximal ideal divided by the maximal ideal squared, so the ideal generated by all products of two elements in the maximal ideal. So this is also a vector space, and now we take the dual vector space. So that, so obviously MP is a, so it's an ideal, but in OXP, but it's, if I take MP modulo MP squared, it is a K-vector space, because if I multiply, it's a priori, it would be a module under OXP, But now, if I multiply with any element in OXP, in the local ring, then if it lies in the maximal ideal, it will bring this thing to the maximal ideal squared, so I get 0. So OXP just acts by the part in it's a so it's a K vector space, MP modulo MP squared is K vector space. K, we know is equal to OXP. So, and I take the dual vector space, so TPX equal to this, which, to make it more explicit, I could also say it's a set of linear maps from, say, V, from the maximal ideal to K. So, I mean, K acts on this as, so linear maps from maximal ideal to K, which vanish on MP squared. Okay. So this is, now this is a bit abstract, but it's not so strange. I don't know precisely how you define tangent spaces in differential geometry. Maybe as you used embedded things, it was simpler, but one standard definition is precisely that. You look at the differential functions. You look precisely, the one standard definition of the tangent space in differential geometry is that you take the differential functions near the point P on your manifold, which vanish at this point, divide by those which vanish to order 2, and you take the linear maps from these to R or whatever. This is one definition of the tangent space. And this, somehow this corresponds to the kind of visual notion of tangent vectors by saying that this map is the operation of differentiating along the direction of the tangent vector. Take a curve in your manifold whose tangent vector is precisely this, and then you take so in differential geometry, and then you just take f composed with the curve and you differentiate it, and this gives you this statement. So in that sense, it's precisely the same definition as in differential geometry. As usual, I mean, we have the standard words, P, so we have a P in X is non-singular if and only if the dimension of the tangent space is equal to the dimension of X and the other things that we had. So now we have this issue that we have now in the case of, so if I want to make this definition, there's a bit of problem because I already have made a different definition, and obviously they should be the same. So if I have an affine variety, this definition should coincide with the definition given here, or at least they should give me isomorphic vector spaces for the tangent space, and so we want to see this. So now, so to see both definitions of the tangent space are isomorphic. Give isomorphic vector spaces. And if one looks carefully, they are canonically isomorphic, so that one could view them in some sense as equal. So for the proof, so for now, I denote, so when are they isomorphic? For affine varieties, which is when both are defined. so for now denote small tpx, the old definition equal to the zero set of tp f1 r, when ix is equal to f1 fr. We note this, the old definition of the tangent space. And then we have to show that this tpx that we defined before is equal or isomorphic to this tpx we have defined here. Maybe this will also illuminate the concept a little bit. Okay, this is a little bit, okay, let's just see. So I have to somehow, what we want is to take an element here in this tangent space, so in the zero set of this thing, and associate to it a map from mp modulo mp squared to k. So, definition. Maybe let's say let x find variety, point in x, and let the a equal to a1 to an be a tangent vector in the old sense. So in the zero set of these differentials of the idea. So now we want to associate a linear map which I call maybe dA from mp to k, which has the property that if I restrict it to mp squared, it's the zero map. And so this is the map from one version of the tangent space to the other. And so, so how do I do this? So let H be an element of, say, this maximal ideal. Then we can write H equal to F divided by G, where F and G are some polynomials. This F and G is the class in AX. And then we are here. And what else do we have? So such that F of P is equal to 0 because we are in the maximal ideal and G of P is not 0. So we can do this. And then in terms of this, I want to say what this stupid dA maps H to. And so we put H of A to be the, I take the differential at P of F, I apply it to A, because remember that the differential is just a linear map from Kn to Kn, and divide by G of P. So in other words, explicitly, this is equal to 1 over Gp, sum I from 1 to n, f by dxi at P times AI. So ith component here. Okay, so now there's a few things to check here, if I even want to write down such a thing, because I have defined this thing in terms of representatives. So exercise check this is well defined. So this means two things. For one thing, it doesn't depend on the polynomials f and g, but only on their classes in AX. And it is also okay with the equivalence equation that we have, one can write things like that as a quotient in different ways, because quotients are equivalence classes of pairs. So first one wants to check this is well defined. And this is not completely arbitrary. This doesn't work for any vector in k to the n. This uses that A is a tangent vector. One somehow uses that it's, that it's in the zero of the differentials of all elements in the ideal, and this somehow makes it then well defined if one goes to the class in AX, because an element here is defined up to adding an element in the ideal of X, and the differential of that is 0, and that will prove that. Okay, that's one thing. It's not, this is just a computation. No, it's not particularly difficult, but one has to see that one uses this. And maybe to also, this is not really necessary, but just to give you maybe some feeling that this makes some kind of sense. So in this situation, this dp h of A can also be just obtained by taking, for any such representatives f and g, you just take d by dt in the usual sense at t equals 0 of f of p plus at divided by g of p plus that it's really, you can see, it's really just you take the derivative in this direction. So in that sense, it really, the point, so in the usual analysis sense, so the tangent vector corresponds to taking the derivative along the tangent vector. Okay. So given this, so we have this differential like this. And now if now H is in the maximal ideal, squared, so it is a linear combination of product of elements in MP. Then of at least two, then H is a linear combination. I mean, with coefficients in local ring of products, say H1, H2 with HI in MP. And then you can apply. So again, we can write HI equal to Fi divided by GI, with again fi of p is equal to 0, which is different from gi of p. And then we can apply the Leibniz rule. Namely, if I take dp of h1, h2, this is equal, so one is supposed to divide by the denominator, so this is 1 over g1 of p times g2 of p. And then now we have these polynomials and we apply the Leibniz rule, so this is dp f1 times 2 of p plus dp plus f1 p times dp f2. And remember that the fi of p are equal to 0, so these are all 0. So this is 0. So thus we see that this map indeed vanishes on mp squared. So thus we get a linear map which I call dA from mp mod mp squared to k, which just sends an element. So now like this. Now this means an element in mp modulo mp squared. So dp h of A. So this is a linear map, and it also depends, by definition, linearly on A. Oh? And the map delta from TPX, so the big TPX, which sends A to this dA, linear. Because if you look here, no, it was just, no, this just depends linearly on the coefficients, on the coordinates of A. So this is our map, and now the claim is that this is an isomorphism. As you see, as I said, basically the point is, here all in coordinates, but in some sense it just means derivative along the tangent vector. Okay. Where am I? So, theorem. This map delta from TPX, small TPX, to large TPX, which sends A to dA, is an isomorphism of vector spaces. Okay. So obviously it is a linear map, so that's fine. And now we have to show it's both injective and surjective. So injectivity so let's take any element in TPX, tangent vector in the old sense, and so where P is a point in X. So now what happens if it's in the kernel? So if A is equal to 0, so what does it mean that dA is equal to 0? It means for all elements in MP modulo MP squared, if I apply dA to it, I get 0. So, or in other words, for all elements in MP, if I apply dA to it, it's 0. It's anyway 0 in MP squared. So, so then dP FA, dF at A is equal to 0 for all F in MP. Now I can just write some very special ones which will determine it. In particular, let's say I put Ti to be in the class in say AX of the variable xi, so the coordinate function to xi, minus the ith coordinate of this. So this is an element of AX. But it's also, as you see, at the point P, not xi, pi. Sorry. So pi is the ith coordinate of P. So if I put the point P, if I evaluate this at the point P, then I get 0. So this is actually in MP. So for I, okay, so it's just the ith coordinate, but we subtract pi so that it vanishes at our point, and we take its class in MP. And then, so what do we have? dP Ti of A. This is just we take the it's just dF by dxi times at 0 of AI. So this is just, by definition, this is just AI. So if this is 0 for all this, for every f, it's also true 0 for Ti, and so it means all AI are 0. Very argument. So now for the converse, in some sense, it's the usual thing. You want to, once you know the injectivity, basically the surjectivity follows because we now know, we have seen here how one can obtain the AI in this way. So let me just, so there's only one way how one can write down something that maps the correct way. And so let's see. So now, so surjectivity. So let we take some element delta from MP to K in this tangent space. And we want to see it's in the image, so we have to find the stupid A that maps to it. So we put A equal to A1 to AN with AI equal to the delta of the Ti we just defined. Now we had just precisely seen before that this gives us back the AIs. So now we can, so therefore it's the only chance how this can be true. So claim delta is equal to dA. So as I said, by definition, and as we had seen, we have that delta of Ti is equal to AI. So dA, where I put obviously A equal to A1 to AN. So now we have to see that this is enough to determine delta. So if we know it for all the Ti, we know it for every element in MP. So thus it is enough to show that MP modulo MP squared is generated as a vector space by the classes of the Ti mod MP squared. No, then that means these Ti are generators of MP mod MP squared. So if I know what delta does on them, I know what it does on the whole vector space. It's all very elementary. Okay, and so we just check this. So if I take an element F equal to G mod H in MP, where G and H are elements in AX, then I can rewrite this. So 1 over H of P times G, so obviously H of P is different from 0. 1 over H of P times G is actually an element in AX, because I just have multiplied by a number. And if I take 1 over H of P times G minus F, I can just write this down. This is, if I'm not mistaken, G times H minus H of P divided by H minus H times H of P. So now you can see G divided by H was in MP. Obviously, H minus H of P divided by H of P is also an MP. So this is an MP squared. So in particular, thus we can see, so thus MP is generated. MP modulo MP squared is generated as a K vector space by classes of elements in AX. So classes modulo MP squared. Okay, so I don't need to deal with quotients. And now all elements, you can easily see that all elements in AX are polynomials in the Ti, just because every element in AX is a class of a polynomial modulo the ideal of X, and obviously a polynomial is a polynomial in the variables xi, and if I take, then I shift back to 0, but otherwise it's the same. and monomials of degree bigger equal to 2 in the TI are in MP squared. So therefore, as a vector space, MP modulo MP squared is generated by the classes of TI. Generate MP modulo MP squared as a vector space. Okay, I made it maybe a bit long, but anyway, this is the story. So we have, okay. Now, it's maybe not very illuminating, but you can see that by some simple calculation you can prove this. And I mean, the proof is, I mean, definition is maybe a bit strange, but if you imagine that it just means this, it maybe is, does make some sense. And here, in some sense, it is rather clear. You just take, you could assume that your point is just a 0 point, then you get the AI as what this thing does to the variables xi. And so this shows the injectivity. And for the surjectivity, you have to see that, you can just take as a vector, you send it, it comes from what it does to the vector whose coordinates are what it does to the xi, and then by this computation, you see that that determines it. Okay. So now just want to make a few more. Okay, so in this context, we can also interpret the differential of a map more abstractly. So the definition of a morphism, let phi from x to y be a morphism of varieties. P and x, obviously. So the differential of phi at P is dp phi from the tangent space of P at x to the tangent space at phi of P y. And we want to do kind of the obvious thing. So we have, what is the tangent vector here? It is a map from MP modulo MP squared to K. And here we want instead the corresponding thing here for phi of P. So obviously, the way how we get a tangent vector here is by composing with phi. So this is sent. So V composed with phi. Because then, see. So we first so we start with the so if you have here so basically we just compose with the pullback. So if this goes from m phi of p divided by m squared. So we have here, now we compose with a function which vanishes at phi of p. If we compose with phi on this side, this is a map from mp modulo mp squared, and then we apply v. This goes to k. Okay, you can try to. And now the exercise is that in the affine case, this identifies with the previous definition of the tangent space. So the isomorphism TPX to TPX identifies this for polynomial maps. With the previous definition. Of the differential. Again, this is just a very simple check. So it's useful to have these abstract things if one wants to prove theorems. On the other hand, if you have a concrete example, most of the time it's much easier to work with coordinates and just do the computation. So therefore, it is also useful to have this. So now, obviously, if we have this definition, it makes it clear that the tangent space depends only on a small neighborhood of P, no? Because it just depends on the local ring. And so if in particular, the tangent space is the same as the tangent space of any open neighborhood which contains P. So by definition, TPX depends only on open neighborhood of P. So thus, if P is in a point in X which is quasi-affine, so an open subset in an affine set, and X bar its closure in AN, then obviously it follows that TPX is equal to TPX bar. But also, if P in X is quasi-projective, and X bar is a closure En, then TPX is equal to TPX bar. And in particular, this allows us for projective varieties to, if we just, normally the tangent space, we want to know what the tangent space is as a vector space, so we can compute it in any affine chart. So we can just take our point P will lie in one of the UI, we just compute it there. So we can always reduce to the affine case. So in this case, choose an I so we NPN in 0 n with P lies in UI. That means And then the tangent space TP X will just be isomorphic to T phi of P of X intersected UI, where phi is the usual map from UI to AN, and just you have 0 to xn maps to x0 divided by xi until xn divided by xi. And x intersected UI lies in AN. So we have reduced to the fine case. In particular, one can in principle always assume that this I is equal to 0, and then it's just like you did in one exercise, has to do with the dehomogenization of the ideal. So assume if have P is in U0, you can write P is equal to 1 A1 to N. So let X be the ideal generated by F1 to Fr, where the Fi are homogeneous. And we know that maybe I now just write this as X intersected AN. I mean, this phi 0 applied to X intersected U0. So then X intersected AN is the zero set. I think actually also the ideal. X intersected AN is just ideal generated by the dehomogenization of F1 until Fr, where Fi A is equal to F of 1 x1 to xn. And so thus the tangent space at our point P of X will be isomorphic to the zero set of the differentials d at A1 to AN at of F1A d A1 to AN of FNA. Okay, so you can make it, everything is very explicit and can be quite simply. And you can compute in the projective case in the same simple way as in the affine case. So let's just look at one little example. So let's say that X is the zero set of, say, well, anyway, still write it like this: Z times y squared minus x to the 3 in P2. Okay, so now I want to know what are the singular points and non-singular points, so the tangent space. So we have the one chart when, so the Z is for me now the zeroth coordinate, so one is when the Z is non-zero, then I can normalize the Z to be 1. So when Z is equal to 1, then we are in the chart U0. This is the zero set of y squared minus x to the 3 in A2. and this is our usual cuspidal curve. So this has a, thus, in this chart we have the only singular point is in this chart the point 0, 0, which in the projective space is the point that means 1, 0, 0. So if z is the zeroth coordinate. And when instead we have that, which one do I want? When y is equal to 1, then this is another chart. This is the zero set of z minus x to the third. So in this other, in another copy of A2, you can see this is a non-singular. This you can easily check that this is non-singular because the derivative by z is always non-zero, the partial derivative. So this is non-singular. And finally, you can easily check when you are outside these two charts, so which would mean that both z and y are equal to 0. When z is equal to y is equal to 0, there are no points of x there. The point does not lie on x. No, there's no solution for this equation where both z and y is equal to 0. If z and y is equal to 0, then x has to be 0. And so this completely describes this thing. And so we see altogether this has one singular point, which is the point 1, 0, 0, and which is a cusp, as you can see from this affine picture. What? Okay. Can also so I will want to prove that every variety has an open dense subset of non-singular points, generalizing the thing we proved for hypersurfaces. And so first I want to again call to you the Jacobian, which you already in some sense used. So the Jacobian of some elements f1 to fr in kx1 to xn is, as we had seen, is just J, is the matrix J of f1 to fr, which is the matrix of these partial derivatives, df1 by dx1, df1 by dxn, and dfr by x1 until dfr by dxn. This is this matrix, and note we had seen that if we take the no, this maybe not the point, but so note if X in AN is a fine algebraic set with the ideal of X given by F1 to FR, then the claim we had, the claim was that the definition was the tangent space. Now I write it also in the tangent space of X at a point P. This was just the common zero set of dp f1 until dpfr. But notice that this just means dpf1 is just it's just this linear map and so on. So the common zero set is just the kernel of this matrix. The kernel of the Jacobian of f1 to fr evaluated at p. So we see it's a kernel of such a map, and so we want to use that in a moment. And now I want to prove, maybe as a last thing today, that set of non-singular points of a variety is open and dense. The following theorem. Let X be a variety, and then first, the set of regular points in X is an open dense subset of X. And the second statement is, well, so for all points P and X, if I take the dimension of the tangent space of X at P, this will always be bigger equal to the dimension of X. So our definition for a non-singular point was, so according to our definition, the dimension of the tangent space could be bigger or smaller, and if it happened to be equal, it was a non-singular point. But as a matter of fact, the dimension of the tangent space is always bigger or equal, and the singular point is one where the dimension of the tangent space is bigger. It can never be too small, it can only be too large. Okay. So first we can reduce ourselves easily to the fine case. So X has an open cover by affine varieties. And we want to check something at every point in X. So therefore, it's enough, we can replace X by an open subset in the cover, which is in this affine cover, so which is an affine variety. So thus, we can assume that X in, say, AN is an affine variety. We want to check so that if in every open set, this is an open, in every open subset of this cover, the intersection with X reg is an open dense subset, it means it was an open dense subset. And if every, if we take any point P in X, we take an open affine neighborhood of it, and then we work with that and we check this. Okay. So therefore, we can use work in the usual concrete way, just with the coordinates and with the Jacobian and so on. So let's see. So let's assume that the ideal of X generated by some elements f1 to fr, fi are polynomials. And we know that we had just seen that the tangent space of X at P is the kernel of the Jacobian of f1 to fr at P. Thus, so the dimension of the kernel is bigger if the matrix drops rank, and so this actually is a closed condition. So thus, for any D, if I look at the set, say xd, which is a subset of x, so the set of all points p in x, such that the dimension of the tangent space of x at p is bigger or equal to D, this is a closed subset in X. Why? Because it's the zero set of the of suitable minors of this Jacobian. Because yeah, but I maybe I will go back because I skipped step, and that maybe not particularly useful. So thus the dimension of the tangent space of X at P is equal to the dimension of the thing where the map starts minus this minus the rank. So it's n minus the rank of this Jacobian. Okay. So now, thus, for any D, if I look again, xd, the set of all points p and x, such that the dimension of the tangent space is bigger or equal to D, this is a closed subset in X. No, because it is a zero set. X intersected the zero set of the n minus d bigger equal or bigger, say n minus d I'm off by 1, but anyway, minus of the Jacobian. So if it's so I think it's n plus 1 minus d times n plus 1 minus d. No, because it should be bigger equal to this, and this minor is then this makes the rank smaller. This makes the rank here smaller, equal to n minus d, and so that is right. Okay, and so it's a closed subset because this is a matrix whose coefficients are polynomials, and the minors are just polynomials, and we have the zero set of those. So we know at least that this is closed. These sets are all closed. So we choose the largest D such that if I take x, d is equal to x. No? We are requiring that the dimension of the tangent space is bigger or equal to d. If we take d small enough, then or could take it minus 10 or whatever, then it's certainly the whole of x. And when we make it larger, there will be a last time when this is still the whole of x. Then I could call x0 which is equal to x minus xd plus 1, is an open dense subset. No, because xd plus 1 is a closed subset of x and it's not equal to x. And now we want to see, so we have to show that D is equal to the dimension of x. Because then, first, we have that x0 will be equal to x reg, so the regular locus, because D is the dimension of x. And maybe I can do it in the other order. So the first is then the dimension of TPX bigger equal to the dimension of x for all D in x. No, because that's precisely, now this is D, and we had precisely said that xd is equal to x, where D is the dimension, so at all, we have this. And secondly, if we take x0 equal to x minus xd plus 1, this is the locus where the dimension is where the dimension of the tangent space is precisely equal to the dimension of x. Second, x0 equal to a set of all p in x, such that dimension of TPX is precisely equal to D. But this is equal to the dimension of x. So this is x reg. And so we would have shown that both statements, the dimension of the tangent space is always bigger than the dimension of x, and the set of regular points is open and dense. Okay, and now we have to see this last. We have to prove this little thing. So we know that we had shown the other time that x is birational to a hypersurface. We want to reduce it to the case of hypersurfaces. In a the dimension of x plus 1. Oh, we had shown that. So that means that, and we know, so and the hypersurface I may call y. So we know, for hypersurfaces we know the statement. We know that y reg is open and dense in y. This was a proposition we proved before. So we can choose, they are birational, so they are open subsets which are isomorphic. So choose non-empty open subsets. U subset X, V subset Y, which are isomorphic. Maybe isomorphism P from U B. Then intersection of open subsets is non-empty open subsets is still non-empty open, and so therefore dense. So Y reg intersected V is open dense in Y and P to the minus 1 of Y reg intersected V is an open open X, and these points are all regular points. So phi is an isomorphism, so that means phi to the minus 1 of Y reg intersected V is contained in X reg. Well, this in some sense already shows it's an open dense subset, but we also see that so in particular, it contains a point, so in particular the intersection is non-empty, so the dimension of the tangent space at every point here is equal to the here the dimension of the tangent space is equal to the dimension of X, and here therefore it is also so here dimension of T. So thus dimension of Tx is equal to the dimension of T whatever, e to the minus 1 P. Y for all these P I make it, I don't know, I maybe don't have the most efficient for all phi here, and this we know is equal to the dimension of X. And so this shows the claim. Sorry, I went a bit over, and I'm also sorry I was maybe it's not the most efficient way of doing it. It's a very simple argument, and I made it look more complicated than it is. But at any rate, if you want, you can try to say the same in with a few less lines. But it's also maybe an exercise. Okay, so maybe I stop here. So this is there's only one more lecture, but so are there any questions now? Otherwise, I will, I think, briefly talk about non-singular curves. I mean, what they look like, and if I have some time left over, maybe give some more examples, and then yeah, I wish you a nice weekend, and we see each other on Monday, I expect. Tomorrow. Oh, at what time? Okay. So that's good to know. There was some reason why it couldn't be on Monday, I expect. Yeah. Okay, so I have to. Okay. Thanks.